Hello, my name is Jared Skeens, and welcome to the Zoom room. Today, I would like to cover Pure Maths 1, Differentiation, Part 4, Stationary Points and Nature. Now, these are actually two concepts, but they're linked together, so I like to cover them together so that you can see how they're connected. And again, let me remind you of our general flow here. Of our original function is what you use to find coordinates. Our first derivative is what you use related anything to slope. And we've already seen two other applications. We saw the application to tangent and normal lines, where this provides the slope for those equations. We also saw increasing and decreasing functions. And now we're going to move into stationary points and nature. Now we also are going to include the second derivative, which is the same formula, just done a second time. And this is going to provide for us what is described as the nature, meaning it will determine for us whether our stationary point is either a minimum point or a maximum point. So if we look down here at our graph that we looked at last time, notice this red line is representation of a function, a curve. And so in part one, when we did the derivative, that formula, the derivative, allows us to find the slope of any particular point along our curve. We just take the x value, plug it into the derivative, and it provides us the slope at that particular point, whatever point that we choose. Then we moved in part two into the tangent and normal lines, meaning at a particular point, we have a tangent to the point. We also have a normal, which is perpendicular to the point. So again, it could be any point, and we're looking for the tangent line to the point or the perpendicular line to that point. Then in part three, we looked at increasing, decreasing functions. And here again, as you look at the curve, you can see there are intervals. There's an interval over which our function is increasing, meaning it's going to have a positive slope, meaning our first derivative would be greater than 0. It's positive, right? There's also an interval at which our function is going down or decreasing. So that's where the slope is negative because it's going down. So our first derivative would be less than 0. And then again, we have another interval over here where the graph is increasing again. So again, we see how the derivative slope has multiple applications. Now what we're looking at is a stationary point, not any particular point on the graph, but specific points. And these are the boundaries, these points, these stationary points, are the boundaries between the increasing and the decreasing. Notice here you have increasing, then decreasing. Here you have decreasing, then increasing. So this maximum and minimum, these are called stationary points. These maximum and minimum values are at the peak or down at the valley, and it's where the change in slope occurs. So right at that point, it is neither increasing nor decreasing, and that's probably why they call it stationary, because it's not going up, it's not going down, it's at the point of the in-between. And here you have going down and then going up, so the point of change is the stationary point. Now, notice that the tangent to our stationary point, to either max or minimum, is horizontal. Okay, our tangent line to maximum or minimum to these stationary points are horizontal, meaning the slope is 0. So when we're working with stationary points, we want to take our derivative and set it equal to 0, because the slope of the tangent lines at those points are horizontal, meaning has a 0 slope. So when we solve for our stationary point, what it gives us is the x coordinate. So if we have the x coordinate, we could plug it back into the original to get the y coordinate, but that only gives us a location, meaning it tells us how far left or right and up or down from the origin. It does not tell us whether that particular point is either minimum or maximum. We don't know. We just found the location. So then when it says find the nature, it means to determine whether that stationary point is a maximum value or a minimum value. Now, when we say maximum and minimum, it's more correct to call it a local minimum and a local maximum. Notice this curve goes up and up and up. So in other words, it's going to have higher values, but it keeps going and there's no 0 slope up there. It just keeps going up forever. And similarly on this side keeps going down forever. So there are lower values. So what we're looking at is like a local max and a local minimum. Just like maybe you have hills in your area and the hill might be the highest point in your area, doesn't mean that it's the highest mountain in the whole region. So it's just in your local area. That's what we're talking about, min and max, are the high and low points within a local area, okay? So there's actually 2 ways that you can determine the nature, and one of those ways is through the second derivative. So I'm gonna wait and come back to this. Let's get started first and work on locating our stationary point. Then when we get to determining the nature and deciding which one it is, we'll come back and look at this again. So here is our first example, and notice what it gives to us. It does not give to us the original function. It does not say y equals or f of x equals. It says dy dx equals, meaning this equation here is already our first derivative. Okay. Now, actually, there's a I question in here first that says find the original. So in other words, what they want you to do is go from the first derivative and find the original function. Well, we can't do that right now. That's integration, and integration will be the next unit. So after we get to the next unit, you can come back and find that part I where it says find the original function. So for now, we're going to skip that one. We're going to move on to part II, which says find the second derivative. Okay, well, the second derivative is just doing the derivative formula to the first derivative. So this would be the second derivative of the original function. Okay, so it doesn't mean do the second derivative of this one. It's the second derivative of y being the original. But it is one derivative down from the first derivative. So this is the understood first derivative of y, and now this is the next or the second derivative of y. So what we want to do again is multiply to the front. So that's 1/2 5x minus 1, and then subtract 1 from the exponent. That gives us a negative 1/2. And then don't forget this is expanded, so we do the derivative of the inside, which is just the 5. So multiply by 5. Don't forget that step. A lot of students mess up at the beginning of a problem, long problem like this, because they forget the expanded part. So don't forget that. Then your derivative of a constant is 0. So we can rewrite this as 5/2 I'm just going to leave it in, or if you want, you can put it down underneath because it's negative, bring it down, and it's a radical 5x minus 1. So we can put our 5 more center here. So you can write it like that, or you can keep it in its exponential form. Doesn't really matter. So that's our first answer, or the answer to II. Then it goes on and says, find the stationary point. Now, please, every time you look at the question, you need to go back and figure out where you're at and what you want to do with it. So we're finding stationary points. Stationary points is where our first derivative equals to 0. So we don't want to use the second derivative. We want to use the first derivative. So we're going to set that equal to 0. Why are we setting it equal to 0? Because at the stationary points, our tangent line is horizontal, and a horizontal line has slope 0. So we're using, again, the slope concept to set up our equation. Our slope equals 0 at these stationary points. So we're going to solve for the x value of our stationary points. So here we get this equals 0. So we add 2 to the other side. Now we square both sides to get rid of a 1/2. You multiply it by 2, or in other words, you're squaring it. You square a radical, a square root, to get rid of the square root. So the 2's cancel, leaving you with just 1. And now you end up with 5x minus 1 equals 4. Add 1 to both sides. 5x equals 5. And now we can divide both sides by 5. And we see that our x equals 1. So this gives us the x coordinate. Now, it asks us to find the coordinates of the stationary point. If you look at the question, it says point, singular. So there's only one stationary point on this particular curve. Some curves, like this cubic, have 2 stationary points, so you would get 2 values of x. This one only has 1 stationary point and has 1 value for x. So if we're actually finding the point, our point would be 1 something. Now, right now, we can't calculate the y value because we don't have the original. If we had done part I, we would have found the original function and we could plug 1 into it and find the y value. We can't do that yet because we haven't got to integration. So you'll have to wait and come back later and find that y value. So for now, we'll just leave it blank. We found the x coordinate. That's what's important for now. Then it says, determine the nature. So look at our verbs here. Find the second derivative of y. Here was the first derivative. Here's the second. Find the stationary point we have, or at least the x coordinate part. And now we want to determine the nature. That means, is it a max or a minimum? We don't know. We don't get to see the graph. We know the location, but we don't know if it's a high point or a low point, if it's a maximum or a minimum. So we need to do a test. There are 2 ways that you can do this test. One way is by doing it through the first derivative, okay? So I'll just show you how that works, but it's not going to be the main way that I suggest. There are times when you'll want to do it this way. I'll explain that in a minute, but let's see how this works. So what you're going to want to do, similar to our quadratic inequalities, it's kind of similar to that, where you're going to take a number line and you're going to take your stationary point or points, it doesn't matter how many, and you're just going to put it on your number line. So here's 1. That means this is the location where our derivative is equal to 0. Now, I'll put it up here just a little bit higher. What we want to find out is whether this is maximum or minimum. So if we use the first derivative test, what we can do is we can pick a point to the left and to the right. So let's say we pick the point 0. It's an easy number to work with. And we plug 0 into the first derivative. We get 0 times 5 is 0. Well, guess what? We can't take the square root of a -1. So it looks like we can't use that. Maybe let's take 1/2. Maybe we can try 1/2. Or we can take 1/5. If we solve that for 0, we get 1/5. Normally you could take 0, but in this particular equation we can't because we end up square rooting a negative, meaning there's a domain issue here that's not presented for us. So we could take 1/5, that's still less than 1. If you put 1/5 in here, 1/5 of 5 is 1, 1 minus 1 is 0, square root of 0 is still 0, and we end up with a -2. That means we have a negative slope, meaning our function is decreasing to that stationary point. If we pick a value on the other side, like 2, we get 2 times 5 is 10. 10 minus 1 is 9. The square root of 9 is 3, and 3 minus 2 is 1. 1 is a positive number. We get a positive number when we do that, and that means our slope is increasing. So notice if you have a decreasing followed by an increasing, it's a minimum value. A negative followed by a positive. So a negative followed by a positive on both sides of our stationary point means it's going down to the point and then back up. So this would be a minimum value, okay? Maybe I'll put that over here on this other side to give me a little more room. So this is one way of determining the nature, and it's using the first derivative. Now, I'll be honest, the only time I use this method is if the second derivative is difficult to figure out. Usually derivatives, especially when you're working with algebra, the derivatives are quite easy to figure out. So usually I'll use the second derivative test, not the first derivative test, because it's quite easy to find the second derivative. However, now that you've already had some, or I guess later, maybe in Pure Math 3, when you learn derivatives with trigonometry, some of those trigonometric expressions are a little difficult to find the second derivative. So if I'm working sometimes with some of those difficult trigonometry ones, then I won't do the second derivative because it's difficult. I'll use the first derivative test. But that's not until Pure Math 3. So I would say for Pure Math 1, you should be aware that this method is available, but practically speaking for Pure Math 1, the second derivative test will probably, you'll find it easier, okay? So how do we do the second derivative test? Well, the second derivative test means that you need to evaluate the second derivative for the x-coordinate of your stationary point. So here's our second derivative up here. So what we're going to do is we're going to take our second derivative, evaluate it for 1. 1 is our x-coordinate of our stationary point. So this is our second derivative in terms of x. So we're going to evaluate it for when the x is 1. And what we end up getting is 5 over 2 times 1. 5 minus 1 is 4. The square root of 4 is 2. So we end up getting, I'll put it down here, equals 5/4, which is a positive number. So if our second derivative is greater than 0, meaning it's positive, then we make a smiley face. Positives, the eyes are wide open, and it's a smiley face. And if it's a smiley face, it means the stationary point is at the bottom. It's a minimum. Okay? So really what's happening, what the second derivative does is it actually tells us about the concavity of the graph. You like concavity, what is that? Concave is like this. Okay, this is concave down, and this would be concave up. So what a stationary point is it is the boundary, or what a stationary point is it is at the top of either concave up, that's maximum, or at the bottom of concave down, and that's minimum. So notice here's a concave down, and the maximum point's at the top. Here's a concave up, and at the concave up, at the bottom is a minimum. There is one other point that you can be aware of, but Cambridge doesn't really ask for it. And notice that at some point in here, right in the middle here, you change between concave down and concave up. This is what's called a flex point. So flex point is where concave down meets concave up. If you were to solve for where the second derivative equals 0, it would give you the location of the flex point. Cambridge doesn't ask those questions, so you don't really need to know that, but it is kind of an important feature in graphs. If you happen to hear flex point, it's where concave down meets concave up. That's for free. You don't really need it, but you do need to understand maximum and minimum, concave down, concave up. So when your second derivative is positive, it makes a smiley face. If your second derivative is negative, you know, when someone's being negative, they're frowning, so they're squinting their eyes and have that frowny face. And so at the top of the frown is a maximum. So we use smiley face and frowny face from the second derivative to help us determine the nature of the stationary point. So either way, we end up with minimum. Again, this way is sometimes, you know, it's not my favorite. I prefer the second derivative test. We already found the second derivative, so it's much easier, especially in this example, to go ahead and just evaluate it and see if it's positive smiley face or negative frowny face. And this is a minimum. Okay, so here we found almost all the answers to the question. You'll have to wait for integration to find the original. And once you have the original, you could plug 1 into it to find the y value, because the original function gives you coordinates, first derivative, anything related to slope, and then the second derivative for the nature of the stationary point, which is your min or max. So let me set up another example. Okay, here we are with our second example. Now this time they give us the original function. Notice it says y equals x cubed minus 2x squared plus 5x, and it's said to be passing through the origin, which makes sense. If you plug in a 0 for x, you're going to get 0 for y. Now in part I, it says show that there are no stationary points, which sounds kind of interesting. How do you show that there's no stationary points? Well, you need to just follow the concept of stationary point. Stationary point is where our slope equals 0. So let's start with that. We'll start with show our, set our slope equal to 0, and it means we shouldn't be able to solve it. So we'll go with y prime, our first derivative, because that's what we use. Stationary points is about slope equaling 0. Okay, so this here gives us the f prime equals 0, gives us our stationary points. Okay, so we're going to start by taking the first derivative, which is 3x squared. Hopefully by now you're following the pattern. It's not expanded, so minus 4x plus 5. And we need to set it equal to 0 and show that we cannot solve this because we have to show that there are no stationary points. So we go to solve this, and if you look at the factoring, you're going to see that the factors of 3 are 1 and 3, and the factors of 5 are 1 and 5. And you cannot come up with a negative 4, so it doesn't factor. And I kind of doubt that you want to do completing the square. Most students try to avoid completing the square. So you could use the quadratic formula. And if you use the quadratic formula, you're going to run into a syntax error on your calculator because you're going to end up with a negative in your radical in the quadratic formula. So what you should remember at this point, without having to go into the quadratic formula, is when does a quadratic have no solutions? This is talking about number of solutions. There are no solutions. So this goes back to the quadratic unit. And when it's talking about number of solutions, we work with the discriminant, the b squared minus 4ac. So what we want to show is that our b squared minus 4ac is less than 0. That means there are no solutions. So we plug in our b squared, a negative 4 squared minus 4 times 3 times 5, which equals 16 minus 12 times 5, 60, which is a negative 44. So we show that this negative 44 is less than 0. That is negative. Doesn't really matter the 44. What matters is that it's negative. Therefore, no, what we'll call real solutions. Okay, so no real solutions, meaning no stationary points. So that's how you show that. Now it makes an interesting statement here. You have to pay close attention to the wording. It says denote the gradient. The gradient is what I call slope. Some of you use the term gradient. Denote the gradient or the slope as m. Okay, so they're redefining for us our first derivative of the original function. They're now calling it m. So we're going to say that m equals 3x squared minus 4x plus 5, because this is the gradient. So notice it says denoting, which is like how your notation, how you write it, the gradient as m. Gradient is your first derivative. Okay. Then we want to find the stationary point and nature of m, meaning this. We want to find the stationary point of this newly notated function. We are no longer dealing with the original function because it has been redefined for us. So this denoting has to do with notation. And the stationary point and nature are of m, not of our f of x. So now we want to find our first derivative of m, because that's where we get stationary points. So this is now 6x minus 4, and our stationary point is where the slope equals 0. So now we get 6x equals 4, x equals 4, 6. which equals 2/3. So now our stationary point is located at 2/3. And to get the y value, we plug it into the original being the original m, not the original f of x, because they redefined it here. So here's our original function for the m here. So we plug 2/3 in here. 2/3 squared is 4/9. You can do it on your calculator. 4/9 times 3 is 4/3. 4/3 minus 2/3 times 4 is 8/3. So 4/3 minus 8/3 is a negative 4/3. And this 5 is a 15/3. 15 divided by 3 is 5. So a negative 4/3 plus 15/3 is 11/3. If you're good with fractions, but actually, I wouldn't recommend you do it in your head. I would recommend you actually do it in your calculator, plug in 2/3 into your function, and you get your stationary point, singular, is 2/3 and 11/3 for the y value. So that's our stationary point. Then determine the nature. So we're going to go ahead and find the second derivative of m, which is now just 6. Now notice over here, we evaluated our second derivative for a value of x. The thing is, the x's have disappeared. So there's no x to put our 2/3 into. What this means is for the entire function, for the entire original function, it's all positive. 6, it will always be 6 no matter what your x value is, meaning it's greater than 0. Positive, meaning this whole thing is a minimum value, okay? Because it's positive. So in other words, the entire function here is a concave up graph. Now, if you stop and think about it a little bit, what is our original function? M. Our original m is a quadratic. Quadratics make parabolas. This is a positive x squared, means our parabola is going up. The entire parabola is concave up, meaning the stationary point is the vertex. So what we just found is actually the vertex of our parabola. So now you've learned a new way of determining vertex, because the vertex is a minimum, or if your parabola is facing down, a maximum. You can use the first derivative to find the location of your vertex of a parabola. And then the second derivative confirms that your parabola is concave up, therefore the vertex is a minimum, okay? So that's what's important with this. Also notice, if you go back to the original function, the f of x or y, this one would be the first derivative, meaning this one in connection to the original function up here would actually be the second derivative, and this one would be the third derivative. So when you're talking about the number of derivatives, you need to pay attention, where's your starting point. So if it was from the original, it would be first derivative, second derivative, third derivative. But what they did was they redefined the first derivative as m, and then asked you to find the stationary point from there, which is one derivative down, and then the nature, which is two derivatives down from here. So this denoting your gradient as m means notating this now as m instead of as y. So this helps you to understand where you're at in this flow of thought, which allows you to know what kind of information you can get from it. Okay, so another important type of question there. Now let me put up another example. Okay, here's our next example. Now this time they provide for us the stationary point. The stationary point is located at 3 and 9.5, and they do not give us the original function. Instead, they give us the first derivative, the dy dx, equals, and now there's a variable in here, ax squared plus a squared x. And it tells us that a is non-zero. Now, anytime you see something where the constant is like positive or not zero, you should just keep that in mind because it means it's important to the problem. And so they give us the first derivative, they give us the stationary point. So it says find a. So let's do that first. Now, how do we find a from a derivative and a stationary point? Well, remember, stationary point is where your first derivative equals 0. So if we put our first derivative here and set it equal to 0, and we solve it, it will give us the x coordinate of the stationary point. Well, here is the x coordinate of our stationary point. The x value is 3. That means we already know what the x is. So we can put a 3 squared plus a squared 3 equals 0. So because stationary point is where first derivative equals 0, and we already have the answer to x and the x coordinate of the stationary point, we plug that in. So now we get 9, actually if we do this first, we get 3a squared plus 9a. So I just put it in decreasing exponential order, equals 0. This now can factor. So if we take out a 3a, we get a plus 3 equals 0. So that leaves us with either 3a equals 0, which means a would equal 0, and we already see that a is non-zero, so that option is thrown out. And with a plus 3 equals 0, a equals a negative 3. So this is our value for a. So now we can write our first derivative as a negative 3x squared, and a negative 3 squared is 9 plus 9x. So this is now our first derivative statement by plugging a back into here. So negative 3x squared, negative 3 squared is 9, so plus 9x. Now, again, there was actually an II in here that asked us to find the original function. Again, when you're going up in this direction from second derivative to first or from first to original, when you go up, you're integrating. When you go down, you're doing differentiation. So we can't do II yet because integration is the next unit. So we skip that for now. Then in part III, it says determine the nature. Well, of course, nature is referring to our stationary point. We already have the value or our location of the stationary point. So what we want to do now is we want to find the second derivative. Nature has to do with second derivative. All of this is nature. Maybe I'll put that over here. Identifying it as either minimum or maximum. So we need to find the second derivative. So if we keep our notation to match theirs, d2y over dx squared equals, and we get a negative 6x plus 9. So multiply to the front, subtract 1, multiply to the front, subtract 1, you get negative 6x plus 9. And we want to evaluate this for when x equals 3. Okay, so we're plugging in a 3 here. It's the same thing as if you wrote say f double prime of 3. Okay, so this is writing it in function notation. This just shows you're going to evaluate this with x equals 3. Same thing. So when you plug our 3 in here, we get negative 6 times 3 plus 9, which is a negative 18 plus 9, which equals a negative 9, which is less than 0. Again, it's not the number that we're looking for. It's whether it's positive or negative. So a negative 9 is less than 0, meaning this is a negative, and a negative gives us a frowny face, meaning that our stationary point is a maximum value. Okay, so whatever this curve happens to be, this particular point is located on a local maximum. So we found A, we determined the nature. This time they provided the stationary point in the first derivative, and we were able to solve for these missing pieces. And again, in order to find the original, you'll have to wait to integration. So let's look at one more example and see how we do. Okay, here's our last example. Now this example is more like a story problem. It's almost like a practical application. Instead of using x's and y's and just finding stationary points and minimum and maximum of, purely algebraic concepts, now it's applied to kind of a real life situation. How can we actually use this information in helping us solve real life problems? So with this, I didn't write out the whole problem, but it talks about this factory, this machine factory. It produces cardboard cones. And so the equation of the volume of a cone, hopefully you remember from past volume problems, the volume of a cone is 1/3 pi r squared h. Okay, 1/3 pi r squared h is the volume of a cone. And this particular machine has a relationship between the height of the cone and the radius of the circular bottom. And this relationship is that the height plus the radius has to equal 18. So this is like a restriction, maybe because of material or maybe because of the machine itself. But this is a restriction that limits the range of both height and the radius. And the combination of the two have to add up to 18. So here in the first part of the question, it's a simple algebraic exercise. It says to show that the volume equals this. So what they're doing is in your volume of a cone, you have two different variables, which makes it more difficult to work with. So what we're going to do is we're going to put everything in terms of r and just eliminate the height. Once we find r, we can come back and find height later. So what we want to do here is we want to get r by itself. R equals, we want to get h by itself. We want to put height in terms of r. So equals 18 minus r. So when we plug that into our formula, we get v equals 1/3 pi r squared times the height, which is now 18 minus r. And when we solve that, we get 1/3 of 18 is 6, so that's 6 pi r squared minus, and then times the r, we get 1/3 pi r cubed, which is exactly what they have here. So all we did was get h in terms of r. Now we're only dealing with v. This is like v of r, if you put it in function notation. V of r is like f of x. Okay, so volume is our function, and it's in terms of the radius. So the radius is acting like our x variable, and the v is like our y variable. So this is the dependent variable because it depends on what all of this calculates up to. And the radius is our independent variable. That's the one that we're going to solve for. Okay, so here's our first answer, and that's simply just removing the h so that we only have one variable to work with. Now we want to find, again, a non-zero r that is a stationary point. Okay, so we know that stationary point is the first derivative. So if we take the first derivative of our volume function, we get, and remember the radius is our variable. So multiply to the front, we get 12 pi r. So multiply to the front, subtract 1. Here we multiply to the front, subtract 1. So the 3's cancel, minus pi r squared, because you subtract 1 from the exponent. So 3 minus 1 is 2. Okay, and to find the stationary point, we set this equal to 0. Stationary point is first derivative set equal to 0 because the min and max has a horizontal tangent line, meaning the slope is 0. So now we take this, we can factor out a pi and an r. So if we take out pi r, that leaves us with 12 minus r equals 0. So that's pi r equals 0, where r cannot equal 0 because we already said non-zero r. Doesn't really make sense to have a 0 radius anyway, right? If you have a cone with a 0 radius, your cone is all height. Doesn't really, not very practical for a cone. So here we have 12 minus r equals 0, or r equals 12. So when r is, notice 12 can be a lot of different numbers. You could have 9 and 9 add up to 18. You could have 10 and 8. But when r is 12, meaning h would be 6, that is a stationary point, meaning it's either a minimum volume for your cone or it's a maximum volume for your cone. So now it says, show that it's a maximum. Okay, so that means we need to do the second derivative here. So if we do the second derivative, I guess I can do it in red here. So the second derivative would be 1 times 12 pi is 12 pi. So then the 1 minus 1, the r cancels. Here, multiply 2 to the front, minus 2 pi r. Okay. So we're going to evaluate this when r equals 12. So when r equals 12, we get 12 pi minus 24 pi, which equals a negative 12 pi, which is less than 0. Less than 0 is negative, meaning we have the frowny face, meaning this is a maximum. Okay, so our stationary point is at the top of our frowny face. So this is indeed a maximum value. Now it says find the maximum volume of a cone that can be made. So do you start seeing how this calculus can be used? Hey, we have this machine that creates cones. Well, we know the volume of a cone. And we know that there's a particular limitation, whether it's by material or based on what the machine is capable of making, that this relationship has to be 18. So by simple algebraic rearranging, and then by using our calculus, we can figure out what value r should be. We can set the machine to produce the biggest size cone possible. So if we want the biggest cone that that machine can make, we can figure out, and we see that when the radius is 12, meaning the height is 6, that will give us the largest volume, if volume is what you want to maximize, okay? So let's now find that maximum value. So we come back to our original equation here. And so we're going to get volume. Let's find the volume when we have 1/3 pi 12 squared, that's our radius, times 6. And when you multiply this out, you can use your calculator. When we multiply it out, we get 288 pi, which you could leave that as your answer. It would be acceptable. But that doesn't really give us an understanding. So it also equals 900, it's like 904.7. But to 3 significant figures, 905 to 3 significant figures. So if we're dealing with, say, centimeters, then the volume would be 905 cubic centimeters, because volume is third dimension. So radius would be one-dimensional. Height is also one-dimensional. So the radius of our circle would be 12. The height would be 6. And when you find the volume of that cone, you would have 905 cubic centimeters, or whatever the units were of the radius and height. And so this then, either one of those forms would be correct. This then is your maximum volume. So I hope as you learn algebra or calculus or trigonometry or geometry, math is a system. It's a mental construct, but it's used to model reality. So in other words, math is both a discovery, that we discover these principles in nature, and it's also an invention, as the notation is invented, the mental construct to represent those principles of nature are invented so that we can run the math and come up with solutions to real life situations. So I hope you enjoyed it. Again, thanks for joining me, and see you again next time for part 5, where we finally look at how we can work with these differentials.